So begins Lecture 3 on the Binomial Theorem. This is taken from pages 22 to 30 of Rotman's Journey into Mathematics and Introduction to Proofs, which is a nice little book available by Dover. So here we go. So first of all, look at 1 plus x to the 0 power. Well, that's 1. Look at 1 plus x to the 1 power. That's 1 plus x. 1 plus x squared is 1 plus 2x plus 2x plus x squared. And 1 plus x cubed is that. And 1 plus x to the 4th is that. And 1 plus x to the 5th is that. All right, straightforward polynomial algebra. But the neat thing is that you can start to see that there's a pattern to the coefficients which appear here, right? Like the coefficients 1 and 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And if you look at that, you notice that there's a pattern. The inside numbers are always obtained by adding the two numbers above, right? So 1 plus 2 gives me 3. 1 plus 3 gives me 4. 4 plus 6 gives me 10. And so this is known as Pascal's triangle, all right? But truth be told, it is older than Pascal. Rotman has a lovely picture of something similar in here. And this is a picture from a Chinese illustration made in 1303. So here's, well, it's Pascal's triangle, right? You see the Chinese symbol for 1, 2, 3. Hey, look at how easy Chinese numbers are. Look at that. 1, 2, 3. 3 plus 1, that's the symbol for 4. 3 plus 3, that must be 6. So that's kind of neat. You could learn some basic Chinese numbering just from staring at this for a bit. But cool. Anyway, so that predates Pascal by a couple hundred years. And honestly, I would not be at all surprised to find that this was known to other ancient civilizations, because it's pretty basic, really. And as we'll see, it ties into certain questions of counting, which would have been of interest to people of various different civilizations. So it wouldn't have been surprising for other civilizations to discover this. So here's how we go. So we say 1 plus x to the n. We're going to define coefficients for that to be c0, c1, da, 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 all the way up to cn. All right? And so let me just uncover it there. So what's going on here is we're defining this symbol n choose r to be the coefficient cr, which is found next to x to the r in 1 plus x to the n. All right. So for example, if I look at 1 plus x to the 5th, so like 1 plus x to the 5th has coefficient of 5 next to x to the 4th. So 5, choose 4 is how that's read, is equal to 5. And of course, a coefficient of 5 is also seen, where else? Sorry, I was down below the screen, my bad. So 1 plus x to the 5th has a coefficient of 5 next to x to the 4th. All right, see that right there? Where else is there one? There's a 5 over here. So that would be 5 choose 1. So 5 choose 1 and 5 choose 4 are both equal to 5, because those are the coefficients which appear in 1 plus x to the 5. That's his starting point. All right? And so the theorem, the first theorem, is that, hey, we can get n plus 1 choose r by adding n choose r minus 1 to n choose r, which is just the rule we saw in the triangle up above. All right? So let's see how that's proved. So here we go. Sorry about that. All right, so since we defined and choose r to be the coefficient of CR and x to the r, coefficient of xr and 1 plus x to the n, we just need to show that if we look at 1 plus x to the n, the coefficient of x to the, excuse me, I lost my track. We just need to show that the coefficient of x to the r in 1 plus x to the n plus 1 is CR minus 1 plus CR. So here we do this calculation, you multiply it out, and when you do that, you see what you get is C1 plus C0 next to x, C2 plus C1 next to x squared, and so forth. That's exactly the pattern we want, because next to x to the r, we've got CR plus CR minus 1, which means that when we go back to the n choose r notation, we have exactly this relation. All right, so now here's another little picture that maybe helps this sink in more. So here's Pascal's triangle. I've made the numbers in purple. Here's the corresponding n choose whatever that it corresponds to here. N choose 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4 are respectively 1, 4, 6, 4, and 1. 5 choose 0 is 1, 5 choose 1 is 5, 5 choose 2 is 10, 5 choose 3 is 10, 5 choose 4 is 5, 5 choose 5 is 1. And as you can see, illustrating the theorem we just proved, if you add 4 choose 0 to 4 choose 1, you get 5 choose 1. Right? This plus that gives me that. Likewise, that plus that gives me that. That plus that gives me that. And that plus that gives me that. So, aren't pronouns great? So, moving on. Now, outside of Rotman, if I'm left to my own devices, I tend to define the n choose r symbol by this formula, namely n factorial over r factorial times n minus r factorial. And this is due to Pascal, who lived 1623 to 1662. Huh, that's a ripe old age of, if I've done my math right, 39? Oof. I'd be dead. Anyway, so I don't know if you remember or not, but n factorial is a notation for a rather special way of combining numbers. Like 0 factorial is 1, 1 factorial is 1, n plus 1 factorial is defined recursively by n plus 1 times n factorial, right? So like, just to rattle off a few of those here before I go on. Let's see here. So like, that makes 2 factorial equal to 2. 3 factorial is 3 times 2, which is 6. 4 factorial is 4 times 6, which is 24. 5 factorial is 5 times 24, which is 120. 6 factorial is 6 times 120, which is 720. 7 factorial is, let's see here, 4,900 plus 140, so I think that's 5,040, and that's where I stop. Okay, so as you can see, factorial, it gets real big real fast, but it comes up a lot in calculus too, if you remember. Okay, so anyway, we're going to prove Pascal's result here by induction, all right, like we learned last lecture. Actually, I hope you didn't learn it last lecture. I hope you knew it from other previous work, honestly. Goodness gracious. But so by induction on n, so the base, this is for n greater than or equal to 0, so our induction starts at 0. It's easy to verify that this formula reduces to 1 when we look at n equals to 0, which is good because 1 plus x to the 0 is 1, which means that we need to get 1 because that's the coefficient of x to the 0. Okay, so we're going to suppose inductively that the formula holds for n, all right? And then we're going to consider the formula for n plus 1. So n plus 1, choose r, by theorem 1 is n choose r minus 1 plus n choose r, right? And then, by the induction hypothesis, we have n choose r minus 1 was n factorial over r minus 1 factorial times n minus r plus 1 factorial, right? And notice here that minus a minus 1 gave me a plus there. That's why I've got a plus 1. And over here, we've just got straight up the induction hypothesis, n factorial over r factorial times n minus r. It's already as it was written before. And then what? Okay, so then all I'm doing here is just splitting out. See, I've got n minus r plus 1 factorial. So I'm using the definition of the factorial to change this to these two, right? And I'm using the definition of the factorial to trade my r factorial for a r plus words. Hey, wait a minute. Oh, yes, r minus 1 times r. All right, r minus 1 factorial times r. So this is, again, by the definition of the factorial. And then what? Careful, you got a screen. Then I factor out a common n factorial, r minus 1, and r minus 1 factorial, n minus r factorial. And I'm left with 1 over this guy. And this one just leaves me the 1 over r, right? Excuse me. Then make a common denominator, add them together, cancel out the r's. Oh, sorry, it's horrible. N plus 1 over that. And then what I do is I take one of these r's and I put it over into there. Here, I'll do some color coding again. Give me a second here. So I take this guy here, and that guy there, and I put them together to give me r factorial. And I take this one and that one, put them together to give me that by the definition of factorial. But then this is exactly what I want. This is the formula for excuse me, n plus 1 choose r. Excuse me, goodness gracious. So sorry. The secret word for today is pirate, as in yar. Okay, great. Moving on. So there we go. That's theorem 2 due to Pascal. There are two easy corollaries which come from that. Corollary 1 is that, let me cover this up here. 1 plus x to the n is exactly sum r equals 0 to n of n choose r times x to the r, which we could rewrite in terms of that lovely formula. Okay, that is just literally collecting what we just did, so there's really nothing to prove there. And also corollary 2, which is actually the binomial theorem, for which this lecture is titled. And so it says for all numbers a and b, and n greater than or equal to 0, a plus b to the n is sum r equals 0 to n, n choose r times a to the n minus r, b to the r, which, you know, if you're looking at this, the sum of the index, sum of the powers here, are always what? N minus r plus r, which is just n, right? So another way to write this sum is just I plus j equals to n. N choose I, a to the I, b to the j. Oh, I think I need... Oopsie. See, I was changing the letters in Rotman, and I just got myself almost into trouble, but I'm going to fix it right now. See, be careful. The r here has to go with that r there, so I really, to be safe, I should put a j here. Alright, sorry it's a hideous j, but there it is. Now the proof of that is straightforward, but let's go through it just for a second here. Because I want to give you proofs of some of these things. Alright. So using the notation 0 to the 0 equal to 1, we can easily see the result holds for a equal to 0. So suppose a is not equal to 0, right? And let x equal to b over a. Then we have 1 plus b over a to the n is the sum r equals 0 to r equals 0 to n of n choose r, b over a to the r, right? Which I'll rewrite here again because I made a mistake and it's ugly. So there it is. Then what? Well, we can also do algebra. And algebra says 1 plus b over a to the n is a plus b over a, making a common denominator of a to the n, but then by laws of exponents I can pull out a to the n like that. And then I can take this expression here basically and multiply both sides by a to the n. And that gives me a plus b to the n power is a to the n times that. Then we can bring the a to the n inside the finite sum and use laws of exponents because a to the n over a to the r is a to the n minus r, And voila, there it is, the binomial theorem. So that's pretty cool. I think I first saw this in my Introduction to Proofs class, which was incidentally with Dr. Mohan Pucha, who was he was a fantastic professor at NC State. I really enjoyed Dr. Pucha's teaching. But he also showed us something called the multinomial theorem. But I won't do that in here. I'll just mention there is a multinomial theorem for like adding a plus b plus c to the n, and then there are things called multinomial coefficients. But if you're interested, you can look it up on, for example, Wikipedia, which tends to be pretty good for math, by the way. Yeah, there's something called the multinomial theorem, and it is interesting. If you study the multinomial theorem, you'll find out that there's like a Pascal pyramid or tetrahedron or something. So there's higher dimensional analogs of some of the things we're doing here. But I've never had need of one of those, but that's out there if you want to look for it. Anyway, so getting back on track here, I think I've probably given you a homework problem somewhat like this. So let me do a couple problems kind of like your homework here. Where was I? Yes, I'll scooch this up a bit. So suppose we want to find the coefficient of x cubed y squared and the expansion of 3x minus y to the 5th power. So first order of business, you don't really feel like multiplying this out, right? So we want to use our theorem. We're going to identify a equals to x, a equals to 3x rather, and b equals to minus 1. And so we can apply the binomial theorem with n equals to 5. 3x minus y to the 5th is sum r equals 0 to 5. 5 choose r. See, I've got a to the 5 minus r, b to the r, which with a is 3x and b is minus y. So by laws of exponents, that gives me 3 to the 5 minus r and minus 1 to the r. And then I've got my x to the 5 minus r, y to the r. So you look at that and you go, okay, so to get x cubed y squared, I need to look at r equals to 2, right? So to get the coefficient I want to look at the coefficient of x cubed y squared, which is coming from r equals to 2. So I plug my r equals to 2 into the coefficient right here. Hear me take a second to slightly improve this. So this right here is the coefficient, right? And so this is exactly what's under there when I put r equals to 2. And then, so I've got 3 to the 3, which I think is 27, and minus 1 squared, well, that's just 1, right? And 5 choose 2, we talked about a minute ago, it was 10. And so there you go, 270 there. The coefficient of the expansion there is 270. That's kind of neat. Here's another example. Another example right here. So, all right, so find the coefficient of x to the 71 and the expansion of 3 plus 2x to the 90th power. Oof. Well, definitely you don't want to multiply this out, right? Goodness gracious, you need a lot of paper. So here we're going to identify, we're thinking a is being 3, b is being 2x for the binomial theorem, with n equals to 90, all right? So the binomial theorem is easy enough to write down. 3 plus 2x to the 90th power is the sum r equals 0 to 90 of 90 choose r, 3 to the 90 minus r times 2x to the r power. All right, lovely. And so by laws of exponents, you can pop out a 2 to the r from that. You got your x to the r. So there you have it. We've got x to the r. So now we can identify the coefficient, right? The coefficient of the x to the r, which should be all of this stuff right here, right? So that's what I do. The coefficient, and I set r equal to 71, because that was the question, to find the coefficient of x to the 71. And there it is, 2 to the 71, 3 to the 90 minus 71 is 19, so 2 to the 71st, 3 to the 19th, times 90 choose 71, which is 90 factorial, or 71 factorial times 19 factorial, and that's a pretty good answer right there. Now sometimes these things simplify, so I gave it a shot at it. So like if you write it out, this is, see the 90 over the 71 just leaves me 90 times 89 times 88 times 87 times 86 times 85 times times 73 times 72, and then everything past that cancels with the 71 factorial. And then like downstairs, you still got the 19 factorial, which I wrote out. I thought, maybe if I write all the numbers here, I can see some pattern and cancel some stuff out. But I thought, not really. I'll just leave it. I think this boxed equation is as good as any. I think if you tried to write this in scientific notation, it's pretty big. I haven't tried putting it into Wolfram Alpha, which I don't know if you knew this or not, but you should know this. Wolfram Alpha .com is a great, nice to check large numerics. It's also very helpful for this course because, suppose you want a list of the first, suppose you want a list of all the primes out to like 200. If you just go to Wolfram Alpha and say primes from, primes less than 200, it'll give you a list. All right. Now, beware, I do expect you to do problems using theory. So like if you find a brute force solution of something I assigned by Wolfram Alpha, that is almost certainly not what was intended. But you can use Wolfram Alpha to aid your solution for the, sort of uninteresting part of it. All right. If in doubt, email me and ask me if you're doing the right thing. Okay, so let us turn back to the question of why are we calling it n choose r. So this n choose r business was started by Euler. Apparently, when he first had it, there used to be a divides sort of symbol between the n and the r when Euler first introduced the notation, and then Rotman says it was dropped about 50 years later. In short, if X is a set and an R subset is a subset with R elements, then you can say the number of R subsets of X is denoted by n comma R. This is Rotman's notation. All right, and you could also think about an alphabet with n letters. The number of R letter words with no repeated letters is also n R. Let me give you a short example of that. So suppose your alphabet is, A, B, C, D. All right, so that's your alphabet. So here we're looking at n equals to 4, Then what would if you wanted to look at words, what would, let's say 4, and let's look at 3. That's easy enough. So what are 3-letter non-repeating, no letters repeated words? So you could have ABC, you could have ABD, right? You could have B, let's see here. B, See, I think we're also sorry guys, I think something's, using the word word, it's a little funny here because I think we're not assuming that the order of the letters is wrong book, that the order of the letters is mattering. Let's see here. Let me read it. With a word is a sequence of R letters with no repetition, and with no regard to whether the word actually occurs in some dictionary. For example, the 2-letter words in the alphabet ABC are A, B, B, A, C, C, A, B, C, and CB. So how many R-letter words are there in an alphabet with n letters? Oh, I see. So actually, my bad. I was wrong here. I misread his book. It's the number of R-letter words with no repeated letters is n comma R with times R factorial. I misread it. My bad. Sorry about that, guys. R factorial. Now, so we'll have to fix one of my later examples when we get to it. So, oh no. So, so, oh no. There's a lot of words to do here. Like, oh goodness gracious. So if I've got 4 letters, and so there should be 4. Yowzers. Okay, so 4 choose 3 times 3 factorial, I guess, is what I'm looking for here. There's that many different words. That would be 4 choose 3 is 4, and 3 factorial is 6. Oh goodness, I'm looking for 24 different words. Ay, ay, ay. So, you know, you got BCD. You've got, let's see here. I think that's the different ways you can select the letters. Either ABC, or you've got ABD, or you've got BCD. Is there any other choice? Can I have ACD? Do I have that yet? Just no, I don't have ACD yet. ACD. ABC, ABD, ACD, BCD. All right, so you got these, and then of course you can also like do BCA or CAB or you know, BDA. Anyway, let me not finish this. This is no fun. So if you continue on all the different possible words, there are 24 of these guys. So, sorry about that. You win some, you lose some, you know. So anyway, Rotman explains why n choose r is equal to the number of r subsets of x, where x has n elements, all right? So like, so kind of a fun application of that counting, right? Which, of course, I've not done a very good job explaining here. My apologies. Is that if we look at 1 plus x to the 6th power, which is this, right? There are 6 ways to choose 5 distinct elements from a 6-element set, right? So that's this 6, and that's how I figured that out, all right? There are 15 ways to choose, oh, wrong, dang it. 4, I meant that one. That's the 15, all right. There are 15 distinct 4-letter words formed from a 6-letter alphabet. That is not true. There are 15 times 4 factorial. So I need to multiply that by 4 factorial, which is 15 times 4 times 3 times, 15 times 24, which is big. Let's see, 15 times 24, what is that? So 360. 360 actually. Because I have to multiply the n choose, the 6 choose 4 by 4 factorial. There are 20 ways to select, so that's this 20 here. Is that 20? Well, there's only 120 to pick from, right? So there are 20 ways to select 3 hats from a closet with 6 distinct hats, all right? So anyway, thankfully this is not a class in combinatorics, because I make a lot of mistake with combinatorics, I'll tell you that right now, guys. So sorry about that. I always be leery of my combinatorics. All right, moving on here. Okay, so maybe you remember, maybe you don't, from Calculus 2 that there's something called the binomial series. What's the relation between the binomial series and the binomial theorem? Let's work it out right quick. So to derive the binomial series, you can look at the function x plus 1 to the r. So you can take derivatives, second derivatives, third derivatives, nth derivatives. You can evaluate those at 0, and you get those coefficients, right? Then Taylor series says that the function can be possibly represented by the nth derivative at 0 divided by n factorial times x to the n. So this is technically the Maclaurin series. And so there it is in gory detail out to third order and then the nth order term. And so here it is. 1 plus x to the r is 1 plus rx plus 1 half r times r minus 1x squared. 1 over 3 factorial r times r minus 1 times r minus 2x cubed plus dot 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 until you get to that lovely coefficient of x to the n. So what is this? How does this relate to the binomial theorem? Right? So here it is. So the coefficient of x to the n is this, right? And if you just keep going and multiply by r minus n all the way on to 3 times 2 times 1, and likewise add that down here, well, that's r minus n factorial is what that is. And upstairs, we've completed this to be r factorial. Now, I'm assuming that r is a natural number, a positive integer, a non-negative integer, rather. But the thing is, the derivation up here, the calculus, right? I had not really assumed that r was a number, a positive integer. R could be a half, a third, whatever. R is just a real number. And so this is not finite, right? It just goes on and on. It's a series. And yet contrast that with, of course, the binomial theorem, which is not a series. It's just a finite sum of powers. So how do these two things go together? It's actually pretty simple. When r is a number, this is a polynomial of order r, and so if you differentiate it r plus 1 times, it's just 0. So the binomial series truncates to just give you the binomial theorem in that special case. So truth be told, we could derive the binomial theorem with calculus if you wanted. All right, so that's one thing. And I think it's fun to look at the binomial series just for a second, because it's sometimes a topic which is neglected in calculus too, which is unfortunate, because I think the binomial series was important to the founders of calculus, like Newton, for example, because it gave them a way to calculate, to approximate things like square roots and cube roots and such with a relative efficiency. Here's a calculation to show you where the binomial series converges. Remember in calculus 2, we look at the ratio test to decide the convergence, the interval of convergence for a power series. So when you work out the ratio test, you end up with getting 1 for the coefficients, which implies then that the power series converges when the absolute value of x is less than 1. The endpoints are fussy, and the endpoints depend on the choice of r. I don't want to get into all that, but and also this hasn't proved actually that 1 plus x to the r is equal to that. What we've proved is that this series converges, right? The fact that that series converges does not mean that this is equal to that. To prove that this is equal to that, you have to show that the remainder goes to 0, which is something we almost never do in calculus 2. But to be fussy, you can have a function which has a Taylor series which doesn't represent it, even though the Taylor series converges. So, but anyway, I leave that for another course you take in analysis, perhaps. And here's just an example to finish things up here. So if we look at 1 plus x to the minus 1 power, the binomial series gives us 1 minus x plus 1 half minus 1 times minus 2, or 3 factorial minus 1 times minus 2 times minus 3. All right, putting it into that formula there. And the 2's and the 3's and the 2's, they cancel, and then just get 1 minus x plus x squared minus x cubed, it's like, oh, well, of course we got that, because this is the geometric series with a equals to 1 and r equals to minus x. All right? So there's one example, binomial series. Another example, which is kind of fun, if we look at the square root of 1 plus x, it gives us this lovely series, which simplifies to 1 plus 1/2 x minus 1/8 x squared plus 1/16 x cubed, right? So you could use this series to approximate square roots of 1 plus something if you wanted. This formula is only good if the absolute value of x is less than 1, right? But this is also an alternating series. See that? Plus, minus, plus, it goes plus, minus. And so by the alternating series estimation theorem, that's what that's an abbreviation for, alternating series estimation theorem, if you truncate the series at some term, say this one, it has to be within plus or minus the next term that we didn't use. So if you crunch the numbers here, you get 1.21875. The next thing is about 0.0078, roughly speaking. And you can contrast that if you calculate it just straight with the square root function in my Casio FX115ES. This guy. Then I get 1.224744871. And if you calculate star star minus star, you get 0.006, which is within the alleged tolerance of 0.0078. So, in the time before calculators, these sorts of series were very important. And it's still important to understand them because series is one of the tools we can use to understand delicate questions of number theory. Again, this is more a tool for analytic number theory than algebraic number theory, but nevertheless we do find ourselves sometimes working with series in number theory. So I thought it's good to mention a little bit of these things. But of course, the most important thing for you to do is to finish your homework. So I suggest you go do that. Thanks, guys.